Hello everyone and welcome back to another video. Today I'm going to talk about the relationship between mathematics and rationalism, and why so many mathematicians become rationalists, and why people think about math rationalistically as well. So to begin with, let's start with just this idea that a lot of mathematicians historically who were philosophers became rationalists. You have examples such as Bertrand Russell, Spinoza, Leibniz, Descartes, and all these people were mathematicians. I think Pascal Pascal too. I think he would be considered a rationalist, maybe. Yeah, but all these people were considered rationalists, and they were mathematicians at the same time. These people were both mathematicians and rationalists, and I think this speaks to the way that people view mathematics, and somewhat of the way that mathematics is structured as well. But I think most people view mathematics as this thing that's disconnected from reality, this sort of thing that is just this moving around of symbols rather than actually looking at reality and seeing something that's empirically true. People don't understand the relationship between mathematics and reality. Well, obviously, they are related, since mathematics has to start from reality. All concepts have to be derived from reality, and mathematics corresponds to reality. It corresponds to real things in real reality. Some people discuss problems or discuss things like the imaginary numbers, for example. Well, the thing is, engineers use imaginary numbers all the time. These numbers are useful. These numbers are real. These numbers are... Imaginary is a terrible name for these numbers, because these numbers are incredibly useful in applications, incredibly useful in math, and now they're not necessarily like an actual thing in reality. Like, you can't point to... like the same way that you say, oh, I have one book. You can't point to I books, but it's the same way you can't point to -1 books. There's no such thing as negative numbers either. It's the same principle. These things have been come up with to basically explain reality better, to explain different things that we see in reality with better concepts, to allow you to take the square root of -1 and still make logical mathematical computations and come to results that are reflected in reality. Now, all these sort of things are based in reality, and they apply to reality. They are real things. But a lot of people view mathematics as rationalistic deduction, which to an extent makes sense, because a lot of mathematics is deduced from other math. It's deduced from other mathematical principles. However, it all has to still correspond to reality. Mathematics is constantly checked against reality. And these things that you prove, they have to be coherent, and they also have to be consistent with reality. In mathematics, you are describing things that are real. You are describing entities in reality, things that are actually real in reality. And that's sort of what prevents you from just deducing all these other crazy things that aren't actually true. You have to deduce in accordance to reality. You have certain rules that you have to follow that are reality. You can't just make up whatever the hell you want deductively. It has to be logical, and this logic is based on reality. All of it has to come from reality. All of it has to come from induction from empirical evidence. To know that any sort of mathematical method works, you have to first induce that it works from reality, and then you can apply that method to different different things, like to different numbers, to different equations, to different functions. You can do that once you realize that this method actually works in reality. It's something that you can actually do to things. And math is very, very focused on proving that these things are true in reality. That's a massive, major focus of math. And a lot of people look at math as if it's an analytical truth has no reference to reality, and these things are true by definition in and of themselves without any reference to reality. This, once again, is not true. Don't think about the analytic-synthetic dichotomy. All logic is based on reality. All things that are true are based on reality. And the reason that math is coherent and logical is because it's based on reality, and reality is coherent and logical. Every single concept that you come up with in math starts from reality. It's something that is induced from reality. Every single number, it's induced from the idea that you have, like, I have one book here. This is one. That's that. Then you can basically abstract away the idea of oneness from it, and then you have this concept of one that you can add together. So let's just say entities, for example. This is one entity, this is another entity. 1 and 1 makes 2, and that's how you basically begin with addition. And you can basically get most of math from that, from just looking at reality, from coming up with rules that are based in reality. The ancient Greeks did everything in this regard with geometry. They did everything by simply moving around things in reality, by drawing lines to other shapes in reality. And this is how they basically were able to discover most of math, by doing things in reality. These are essentially experiments, but it's all based on logic as well. It's all perfectly integrated with logic, because there's no dichotomy between the analytic and synthetic. Things that are true analytically are also true synthetically, because what is true by definition, what is true by identity, is true in reality, because in reality things have identity. This is a very important principle. Now, why do most mathematicians who go into philosophy, why do they become rationalists? Well, because they try to treat philosophy like this deductive game, similar to what, not necessarily what math is, but they basically treat math as this deductive game, and then they go and do the same thing with philosophy. They write their philosophy textbooks, they write their philosophy books the same way that a mathematical proof would be written. This is not how you do philosophy. It's not the exact same. There's a sense in which it's similar, because math uses deduction and so does philosophy, but to discover philosophical principles, you need to use induction. Just in the same way that you would discover the concept of addition in math, you would have to induce by looking at reality and seeing how things add together. So that's how you define this concept of addition. It's the same thing in philosophy. When you induce a new concept or a new principle, it has to start with reality. But these people, they try to, these philosophers, these rationalistic philosophers, try to deduce every single principle, which it's similar to how we do things in math, but it's also not exactly the same, because philosophy, you're trying to come up with principles, or trying to come up with general principles, which you need to use induction for. While in math, you're trying to deduce different equations that are logically proven from each other. Philosophy is not the same. You can't do that. You can't start with existence exists and then deduce everything else from that principle. No, you need to use induction. You need to continuously look at reality, and everything still, just like in math, both in math and philosophy, everything needs to stay connected to reality. Everything must stay connected to reality. For both of these things, everything must stay connected to reality. And a lot of these philosophers deduce in ways that they completely disconnect from reality. They pull arbitrary premises, arbitrary methods out of nowhere, and these mathematicians / philosophers, they don't use the same precision in coming at their principles in philosophy that they do when coming at their methods in math. In math, these people are extremely precise. They're extremely precise in making sure that every method that they use comes from reality. It needs to be something possible in reality and something real. While in philosophy, they just go based off their feelings and come up with whatever arbitrary premises they want to come up with, because it seems right, or it seems like it might work, rather than actually inducing it from reality. If they use the same precision that they use in mathematics that they do, or if they use the same precision in philosophy that they do in mathematics, they would discover true philosophy, or real philosophies. But the issue is they try to use the deductive methods that they use in math on philosophy, which doesn't work. Philosophy is a different sort of thing. Philosophy is not... You don't prove philosophical principles the same way that you prove mathematical formulas. That's not how philosophy works. Mathematics does work that way, but all the methods that you use need to be induced to be true. You need to discover that they're true by looking at reality and seeing that this sort of method works. And actually, there's something somewhat related to all of this, like in mathematics. Like, you can't Gödel's Incompleteness Theorem, which I don't know a ton about, and I'm somewhat skeptical on at my initial hearing of this, but Gödel's incompleteness theorem says that you can't prove everything in math simply from the axioms. You need new axioms, essentially. You need to induce new things to discover new mathematical truths. And this is this actually relates to this whole principle of how mathematicians think about deduction. This relates because let's say that mathematics and philosophy are the exact same for a second, and you can deduce philosophical principles in the same way that you can deduce mathematical principles. Well, you can't deduce every single mathematical principle by Gödel's incompleteness theorem. You can't deduce everything from the axioms, just in the same way that in philosophy you can't deduce every single thing from the axioms. So Gödel's incompleteness theorem actually makes it seem that mathematics is more similar to philosophy in this regard, since you need to come up with new axiomatic concepts throughout the science, and you can't deduce every single truth from these axiomatic concepts. You need to still use induction. You still need to use induction to come up with new principles. So math, like philosophy, isn't entirely based on deduction. You can't deduce every single thing. You can deduce most of math. You can deduce a lot of things, but according to Gödel, which I'm still somewhat skeptical of, because everything that we seem to know with math seems to have been deductively proven. But according to Gödel, you should be able to, or you shouldn't be able to deduce every single thing from the axioms. And there's an extent to which that's similar to philosophy, but the assumption in math has generally been that you can deduce everything from the axioms. And when you apply this, when you also apply this to philosophy, and you get systems like Descartes' system, where he starts from I think therefore I am as this axiom, and tries to deduce every single thing from there in a similar way to how a mathematician would try to deduce calculus or different formulas. I don't know, different things from the idea that A equals A, and different things like that. Which also in mathematics, you don't necessarily deduce every single thing from these axioms. Like there's new principles that you need to discover in mathematics, which I've gone into. Like there's different principles that you can apply to different mathematical concepts with this regard, and you need to discover those through induction. And it's the same thing. It's the same thing with philosophy. Mathematics and philosophy are very much similar, but when you view mathematics as a deductive rationalistic game, then you might also view philosophy in the same way. And I think that's how a lot of mathematicians view math. They view it as this deductive rationalistic game that isn't with reference to reality. And you can't blame them, because that's how everybody has trained math. That's how everyone has taught mathematics from the beginning. It's just deductive rationalism. But that's not the case. That's not the case at all. Mathematics is not rationalistic. There is quite a bit of induction that goes into understanding what different methods you can apply to different things. But yeah, I think that is all I have to say for today. I don't know, this whole math thing, this isn't really something that, this isn't, it's hard to find ways to connect math and philosophy, because there's not like philosophical issues that are super closely related to math and philosophy. But there are different things. There are different principles that are involved. Like a lot of mathematicians become philosophers, as I've mentioned in this video. But it's not the same as like, oh, there's this debate regarding quantum mechanics and its relation to philosophy that I can just go jump in on immediately. Yeah, I have to create a lot of new material with this. I have to create a lot of new uncharted territory with a lot of the like relationship between math and philosophy, because it's not something that people talk about all the time, because math is largely uncorrupted. Math is still very dedicated to logic and very dedicated to strict adherence to reality, while a lot of physicists and a lot of scientists are still largely committed, but they're not as committed as they have been historically. And so there's a lot of things that we can talk about with that, a lot of debates that can be had philosophically with regard to this. But with math, there's not as much room for error in this, it seems, from my perspective. So I can't like go and critique mathematicians a lot, because a lot of mathematicians are doing things right. They're proving things that are true. They're discovering truths. But yeah, so I hope this video made sense. I hope that you got some value out of this. But yeah, I think it's important to recognize that math is not a rationalistic game. Math is something that is induced. A lot of it is. A lot of all the different methods that we use in math is induced. We like the idea of what is addition. Well, we have to form the concept of addition. We have to induce different examples of adding two things together and seeing that they form that they work in this certain way. So and it's the same thing with calculus. You have to discover that when you do this certain thing a certain way, you induce that you get this certain principle, and all that sort of things, all that sort of stuff. So all of it is it's not a rationalistic deduction. That's not how math works. Now there's a lot of deduction involved, and there's a lot of moving around symbols, which is fine because these things are in accordance to reality, and you come up with the basic general principles of math. You come up with every single part of math. You basically come up with everything through induction, through discovery, by looking at reality, and then from there you can deduce other things like other formulas, combine things together, get other formulas, and yeah, and then that's how you basically form mathematics. And there's a lot of induction involved. There's a lot of induction of principles and a lot of induction of methods involved here. It's not entirely deduction from a few axioms. That's not really how math is done. At least from my perspective. I'm not super deep into the university yet, and I haven't had all the mathematical education, but yeah, math is something that I love, and it's something that I think I should probably talk a little bit more about on this channel. I'm thinking about starting to do different things related to math on this channel, where I talk about different mathematical principles or different mathematical proofs. Like I have different things in my journal that I've done and proofs related to that I think would be really fun to get out there and make a video on, where I basically go through and explain how I proved everything in my journal. Like, for example, one proof that I worked on for like a week was, now it's obviously all my proofs, I'm very low level in math right now, but all my proofs have been discovered by somebody before. But one proof that I worked really hard on actually understanding was trying to find a function for the cumulative distribution of the normal curve, which basically, to do so, you need to take the integral from negative infinity to x, or to x of the PDF of the normal distribution curve. Which, yeah, I think that could be a fun video to talk about and to figure out and to basically explain my reasoning behind that and how I got to that. And because there's not really any videos on YouTube of that. I was trying to find different things that were like explained how this specific thing was derived, but I couldn't really find anything, which was surprising to me. I thought there would be a lot more stuff on that. And yeah, a lot of higher level mathematics isn't really done that much on YouTube. There's a lot, I guess there is a lot of higher level math, but it's explained in really, really simple ways. It's explained for people with like without calculus knowledge. A lot of it is. Now, some of it obviously is explained for people with calculus knowledge, but a lot of it is explained in ways that, oh, you don't need calculus to understand this, and it's like explained for beginners. So I don't know. I feel like a lot of things that I could discuss and talk about, a lot of different like proofs that I could do would be really fun to do. But yeah, all of this is kind of just an end of video potential update. I think a lot of mathematical proofs would be really fun to do on this channel, and yeah, I'll probably do that someday. I just need to think of a setup. I would need like a new camera to get over my head, and then yeah, I get a whole ass setup. That could be fun. That could be fun. But yeah, I think that's all I have to say for today. So thank you all for watching, and I hope to see you all in the next video. Peace.